So what we have been talking about so far has been Lagrangian mechanics, and after we talked about general coordinate systems and general spaces. So what we're going to talk about or start talking about today and finish up, well, not finish up, there's a lot of things to say about it, but finish up for the smaller course, SI 1142, what we're going to talk about is Hamiltonian mechanics. So just like Lagrange mechanics, Hamiltonian mechanics is a reformulation, if you will, of classical mechanics that can be shown to be equivalent to Lagrange mechanics and therefore also to Newtonian mechanics in some certain cases. As there was a question just before we started, the formulation of Hamiltonian mechanics makes it much clearer how classical mechanics connects to quantum mechanics than maybe Newtonian mechanics does. If one wants to talk about it in that sense, also Lagrangian mechanics also makes it much clearer actually how classical mechanics relates to quantum mechanics, but not using the same formalism. Lagrange mechanics is much more similar to the path integral formulation of quantum mechanics, whereas this Hamiltonian mechanics is much more familiar with much more similar to what you will see in the typical introductory quantum mechanics courses. So to start, when we discussed Lagrangian mechanics, we had typically something like this. So we had some Lagrangian L, which we wrote as some inertia tensor Mij half, and then these generalized coordinates and the time derivatives of those. That's the kinetic energy term. And then we had some potential energy term, which just depends on the generalized coordinates. And what happens in this situation is that in general we end up with a second order system of ordinary differential equations, and the number is of those equations is n, where n is the number of degrees of freedom or number of generalized coordinates. So what you might be familiar with from solving ODEs is that if you have a second order ODE, you can introduce an auxiliary variable to rewrite your second order ODEs as a system of two first order ODEs. And this is essentially the idea behind Hamiltonian mechanics. So we can rewrite this as 2n first order ODEs. And just to give an example of this, so let's make an example. Oops. Let's consider, every physicist loves the harmonic oscillator, right? So let's take that as an example. And for the harmonic oscillator, we have a Lagrangian, which is just m x dot square over 2. So I will have a harmonic oscillator in one dimension. And the potential energy term will be just kx squared divided by 2. Now, this gives us the equations of motion that you're familiar with. The mass times acceleration is minus this constant k multiplied by x. So this is the harmonic oscillator equation of motion. Now, if I introduce an auxiliary variable, which I can call v for velocity, as the time derivative of x, then I can use this equation itself, the definition of v, as one of my first order differential equations, because here we have that the time derivative of x should be equal to v. And inserting this this definition, well, taking the time derivative of the definition and inserting it here, we can write the second differential equation, which will say that m, and if I take the second derivative here, I get that v dot is equal to x double dot. So what I will have is m v dot equal to minus kx. Or if you will, I'm just going to solve for v dot here, is minus k over m times x. So my system of two first order equations are those two. I have expressed the first order time derivative of x and the first order time derivative of v in terms of both v and x. And I can write this as a matrix system. If I let capital X be x v, then I will have that x dot, well, it's going to be a matrix times x. The matrix is going to have zeros there and there, and let's see, x dot is v, so we're going to have a 1 there, and we're going to have minus k over m over here. And if I call this omega, and we say that x at 0 is some x0 and v0, so I'm just going to write x0, then since omega here is constant, the solution to this system is that x as a function of time is the matrix exponential of omega times t times this x0. And so we could solve this system just by exponentiating, because this was a first order system. Any questions on that? Okay, so I mean, this was just an example of how you can introduce an auxiliary variable to rewrite it as a everything as this first order system of two equations. As it turns out, a better choice, or generally better choice, for the auxiliary variable is that we choose some p generally with an index I, just as the generalized coordinates have indices, and we choose that to be the derivative of the Lagrangian with respect to q dot I. So you will recognize this as something we have already talked about in Lagrangian mechanics, and this is called the canonical momentum. Now, if I know both the generalized coordinates q as well as their time derivatives, then I will know what pi is. Conversely, if I know pi and I know q, then I will know how the system is configured at the moment and also how the system is moving at the moment. And once we have introduced this, we get a rather simple form for the equations of motion, because we know that from Lagrangian mechanics that if we take the time derivative of this, so the pi dt or p dot I, that's just going to be d dt dl dq dot I. But if you remember from Lagrange mechanics, this guy is just a part of the Euler-Lagrange equations. And for the Euler-Lagrange equations to be valid, this must be equal to the L dqi. So this is one of our equations of motion in the Hamiltonian formalism. The other equation of motion is going to come from the definition of pi over here, because if we go back to the previous, if we take the derivative here of the Lagrangian with respect to q dot, we're going to get something which contains q dot, and solving for q dot from that equations, from those equations, is going to lead us to the second set of equations of motion. So in general, we're going to have the following. Well, let me actually do that explicitly. So if we look at the oops, sorry. If we look at this minus d dt dl dq dot I, with the particular Lagrangian that we had, what we're going to end up with is something of the following form. So we're going to have the L dqi minus d dt. No, sorry. I don't want to look at this. I wanted to look at the other one. I wanted to look at the different, because this was from the equations of motion. I want to look at this thing. I want to look at the definition of P. So what I have is that Pi is the L dq dot I, but the L dq dot I, that's Mij q dot j, right? And if I multiply here by the inverse of the inertia tensor, which I'm going to write just the m with the indices upstairs, this is going to lead me to q dot k equal to mkj pj. So these are my set of two equations of motion. So we have n equations of this form because I can take any value from 1 to n, and the same is true here, that k can take any value from 1 to n, and therefore I have n equations here and n equations there. And they tell me the time derivatives of the q's and of the corresponding canonical momentum. So the space described by these coordinates, I mean, I can consider a space where I have coordinates q and p. Just as I could have a space described by coordinates q in Lagrange mechanics, which was called configuration space. So pi and qi. So this new space is called the phase space. It's called phase space. So again, where the configuration space describes how a system looks at a particular moment, phase space describes both how the system looks and how it's moving at that particular moment in time. And I can draw how the system evolves in this phase space, and I can do this relatively easily because I know from the first order equations how the system is going to move from every point. So let's take an example of that. So let's go back again to the harmonic oscillator. It will be our favorite example, as usual for theoretical physicists. So I can do that, and I can write here on the horizontal axis, I can put x, and on the vertical axis, I can put p, the canonical momentum corresponding to it. Now, for every point here in this phase space, I know from these equations of motion, I know how I'm going to move from that. So for example, if we look at this harmonic oscillator, of course, in the case of the harmonic oscillator and one-dimensional motion, P is just m times v. So it's just all going to be constant, but we can see then that the derivative of P is going to be negative if x is larger than 0. And at the same time, the derivative of x is going to be positive if the canonical momentum is positive, and negative if it's negative. So this means that for every point here in phase space, I can draw a little arrow to show in which direction I'm moving. So for example, if I'm here on the p-axis, x is 0, so the p derivative is 0, and x is positive, in this case, on the point I drew. So this means that the x derivative is going to be positive. So from here, I'm going to move in that direction. And I can do this for essentially every point, for every point in phase space, and I'm going to end up with something like this. And since it was directly proportional to the coordinate itself, if I do this for all of them positions, I'm going to end up with something like this. And I can also write this one. So this is kind of how my phase space motion is going to look like. So you can kind of see from this drawing of phase space that the trajectories that the system is going to move along is going to be essentially ellipses in this phase space. So let's see if I can draw that something like this. This is how the system is going to move. And as you are familiar with the harmonic oscillator, it just moves back and forth and comes back to the same state again. And this is this you can see here from this phase space drawing. And we're moving around in this direction. Any questions so far? Okay, so let's go on then. So this is kind of how we could rewrite this system of equations as a second order, as a first order, twice the number of equations, but first order instead. So we're going to try to formalize this somewhat and see if we can come up with a way of formalizing it just by itself. I mean, now we based everything on it had to be equivalent to the Lagrange formalism, but we're going to see how this how we can rewrite it as a formalism of its own. So in order to do that, well, I'm still going to connect to the Lagrange formalism, but then we're going to let go of it. So we're going to look at the Hamiltonian, which we have already encountered in the Lagrange formalism, but then we encountered it as the constant of motion if the system is invariant under time translation. So what we had was that H, the Hamiltonian, that was equal to Q dot I dl dq dot I minus the Lagrangian L. Now, when we introduced this this canonical momentum, we introduced it just as this quantity, right? So we can just write this here now as q dot I pi minus L. And now, since we are in the Hamilton formalism, where we have variables p and q, and we want to write first order differential equations, what we're going to do in this expression here is that we're going to use the definition of the canonical momentum to rewrite this q dot in terms of p, because we can do that just using this equation. It's going to let us rewrite q dot in terms of p. And then the Hamiltonian is just going to be a function of p, q, and possibly being time dependent as well. So this is a function on phase space. So h is a function, of q and p generally, and possibly time as well. So we can look at how small changes in the position in phase space is going to change the value of the Hamiltonian. So I'm just going to differentiate here the Hamiltonian. I'm going to insert this definition here when I differentiate. So I'm just going to use the product rule and the chain rule, essentially. So differentiating the first term here, we get pi times dq dot I. Now this dq dot I, remember that I'm seeing q dot here as a function of p and q, but I'm going to keep this dq dot because it's going to turn out that this particular term is going to cancel with another term in the end. And from the first term, I also get this second term, q dot I dpi. And then I have to differentiate the Lagrangian here, which now is going to be seen still as a function of q dot, but we can insert the definition of q dot in terms of p and possibly time. So if I do that, we get the L, the qi, and times the qi, minus the L, the q dot I, dq dot I, minus the L dt times dt. And here I've just used that the function is that the Lagrangian is generally a function of q dot, and t. And now we see here what I just said, that this here is the definition of pi. So this term is going to cancel this term. So what I will be left with here is q dot I dpi minus, and if we look at this term now, let me use red for that, this the L dqi. For an on-shell solution of the Lagrange equations of motion, this is just equal to d dt the L dq dot I, which is p dot I. So the second term here is p dot I dqi. Sorry, we should have the indices in the correct positions. And then this last term, I'm going to keep it as it was, the L dt times dt. So this is the change in the Hamiltonian under a small change in phase space, as derived from the definition of the Hamiltonian in terms of Lagrangian. However, we can also do this computation just from the assumption here that the Hamiltonian is a function of q, p, and possibly time. So if we do that, we just use the chain rule. So what we're going to get is the h, the qi times the qi plus the h, the pi, again, index down, dpi plus dh dt times dt. And now we can compare those two expressions. So this expression here must be equal to this expression. And this must hold for all possible small variations in phase space. So this means that whatever stands in front of qi in one expression must be the same thing that stands in front of qi in the other expression. So what we can see from this is in particular that q dot I, well, that's what's in front of the pi, so that's dh, the pi, p dot I, which is what is in front of, or minus what's in front of the qi here, must be the same as in front of the qi in the other, so that's minus dh dqi. And finally, if we identify the dt terms, we find that the h dt must be equal to minus the L dt. So this last expression here tells us that if the Lagrangian is not explicitly dependent on time, neither is the Hamiltonian, because their partial derivatives with respect to time are proportional to each other. Questions on that? So this thing here are the equations of motion, the Hamilton equations of motion. And given a Hamiltonian in terms of P and Q, this is how we're going to derive the equations of motions for that system. Okay, we have 17 minutes left. So let's just take again the harmonic oscillator as an example. So harmonic oscillator again. For the harmonic oscillator, our Lagrangian again was m½ x dot squared minus kx squared divided by 2. So what we saw was that we got the canonical momentum was just mx dot, and this means that if we want to find the Hamiltonian, this should be q dot p minus the Lagrangian, but where we solve for q dot in terms of p, so well, q, we used x here. So let me exchange this for an x. So x dot p. So this equation, of course, means that x dot is p over l. So if I go here, what I get is p squared divided by m, and inserting this expression for x dot into the Lagrangian, what I get is minus p squared over 2m plus kx squared divided by 2. So for the harmonic oscillator, the Hamiltonian is p squared divided by 2m plus kx squared divided by 2. If I want to find the equations of motion, I use the Hamilton equation of motion. So what I know is that p dot, if I go back here, should be the negative of the derivative of the Hamiltonian with respect to the coordinate x. So I should have minus dh dx, and if I do that derivative, I get minus kx. And similarly for x dot, this should be dH dP. And if I do that derivative, what I end up with is P divided by M, which again is exactly the same equations of motion we got when we just made a change of variables from the Lagrange equations of motion. Any questions so far? You all are very quiet today. Yeah.
Yeah, I was just a bit confused. I think I forgot, but didn't we want it to be like, do we want to look at it from a perspective of only Q's and P's, right? The Hamiltonian.
Exactly.
But we're working with the dots.
Yeah, so anytime I'm writing Q dot here, I'm seeing Q dot as a function of P and Q.
Okay.
So in the translation from the Lagrange formalism to the Hamiltonian formalism, when I do this transformation, I'm using the definition of Q dot in terms of this equation here, in terms of the definition of the canonical moment.
Okay.
So I can solve for Q dot as a function of P and Q, because generally this depends on Q.
Okay, thank you.
Okay, so we're going to go through a bit of formalism now. And that piece of formalism is called the Poisson bracket. And we're going to see that once we have this in place, writing down the Hamilton equations of motion becomes much simpler. So Poisson brackets. So someone said before that this looked a lot like quantum mechanics, and it will look a lot like quantum mechanics, except for that we're going to get rid of I and H bar. So a Poisson bracket, this is essentially a mathematical construct. On phase space. So, and this will, or that will simplify our notation. So I'm just going to go through the definition, then we're going to see how that relates to what we just did. So given two functions, f of q and p and g of q and p, so these are functions on phase space. They are functions of the phase space variables. So we define the Poisson bracket between those two functions. So I'm going to write it with curly brackets. So f, g, curly brackets. This is defined as the f, the qi, times the g, the pi. And remember now that we're using the summation convention, so that here we have a sum over I. Minus the opposite thing, so the g, the qi, the f, the pi. I'm sorry if you hear a lot of noise. There's a truck going just outside the window. But this is the definition of the Poisson bracket, and we're going to see how we can use this. So, but first, I want to go through a number of important properties that this bracket has. So the first one is anti-symmetry. I mean, you see from this minus sign here that if I change the order of f and g, this Poisson bracket is going to change sign. So what we're going to have is an f Poisson bracket with g. It's going to be minus g Poisson bracket with f. This is just changing the role of f and g in this expression. The second important thing to note is linearity. So the Poisson bracket is linear actually in both arguments due to the anti-symmetry. So in general, if I take a constant here, alpha 1 times f1, and I add alpha 2 f2, I take the Poisson commutator with g, because all of the derivatives that we have are linear, the Poisson bracket is going to be linear. So this is going to be alpha 1 f1 g plus alpha 2 f2g. And this follows directly from both of these two derivatives being linear. And since it's linear in the first argument and we have this anti-symmetry properties, of course also going to be linear in the second argument. So the third property is Leibniz rule. And this is going to follow from the Leibniz rule for derivatives directly as well. So in general, if I have here f multiplied by g in the first argument, and I have a third function h in the last argument, this is going to be f times the Poisson commutator of some bracket of g and h multiplied plus the Poisson commutator between f and h, sorry, multiplied by g. So this again follows directly from the corresponding rule for each derivative. And since it's true for the first argument and we have the anti-symmetry property, it's going to be true also for the second argument. And the last one is called the Jacobi identity. And I'm not going to go through it because it takes some time, but essentially it says that it would take f, and then we take the Poisson bracket with a Poisson bracket of g and h, and then we add the cyclic permutations of this. So we add g hf plus hfg. This is equal to 0. Now, this is not hard to show. It's just a bit tedious to show. It essentially involves inserting the definition of the Poisson bracket and seeing how terms cancel out magically.
Can I say something?
Yeah, sure.
This looks strangely like commutators.
Yeah, I mean, it is a commutator in some sense. That's why I did not call it commutator before, but I have several times kind of had a slip of tongue and called it a commutator because this is also called a Poisson commutator in F and G. Yeah. So yes, it is a commutator, and it's exactly this that gives you the relation later to quantum mechanics.
Okay, thank you.
Okay, so these are the important properties that we wanted to have, and in particular, and it's now that we're going to see things that look a lot like quantum mechanics again. So the example here is that we can look at, these are called the canonical commutation relations. I mean, when we have these Poisson brackets, f and g here were arbitrary functions of p and q. There is nothing stopping us from putting f equal to qi and putting g equal to qj or pj. So let's see what happens when we do that. So if we look at the Poisson commutator of qi with qj, okay, so this is going to be the qi, the qk, the qj, the pk minus the qj, the qk, the qi dpk. Now, if I look at these terms, when I take the derivative with respect to the generalized coordinates, this is delta ik, and this is delta jk, right? However, when we're looking at phase space, the generalized coordinates are independent of the momentum. So this term is equal to 0, and this term is equal to 0. So we end up with a 0. And the same goes if we take the Poisson commutator of pi and pj for the same reason. Well, not the same reason, but the reason that the p's are independent of the q's. So the commutator between any two generalized coordinates is 0, just as well as the Poisson commutator of any of the canonical momenta is 0. However, what is interesting is to look at qi commutator with pj. So if we take the Poisson commutator of one of the generalized coordinates with the canonical momentum. So if we write this down, we get the same thing again, dqi dqk, and the second term becomes the pj dpk. Second term is the dp j dqk dqi dpk. Now, in this second term, both of the derivatives are equal to 0. So this guy is 0. However, in the first term, we just discussed that this is delta ik, and this, for the same reasons, is going to be delta kj. And when you do the sum over k here, we find that this is delta ij, which means that the Poisson commutator between a general coordinate and its own canonical momentum is 1, and with any other canonical momentum is 0. So these are called the canonical commutation relations. We have 2 minutes. Let me just do something briefly in those 2 minutes. Let's note the following. So Hamilton's equations of motion which we just derived, we can note that if we take the commutator of qi with the Hamiltonian, this is going to be dqi, dqj, dh, dpj, minus dh, dqj, dqi, dpj. And for the same reasons as before, that guy is 0. The first guy, we have the delta ij there. So what we end up with is that this is equal to dh dpi, which just so happened to be q dot. And we can do the corresponding thing for pi. If we do this and we do the maths, we're going to end up with that this is minus dh dqi, which is p dot I. So in both cases, the time derivative of these phase space coordinates is equal to the Poisson bracket between that phase space coordinate and the Hamiltonian. And it turns out that this is generally true. For any function f of q and p. Now, if we have a function that also depends on t, we're going to have that df dt. If we take the time derivative of f, so this is essentially f dot, we can use the chain rule here. So this is df dqi times q dot I plus df dpi p dot I plus df dt. And what we end up with here is df dqi, and then qi was this Poisson commutator, plus the same thing for the p, df dpi pi h plus df dt. And if you look at what this expression is, we can rewrite this as the Poisson bracket between f and the Hamiltonian plus df dt. So what this tells you is that if f is not explicitly dependent on time, then its time derivative would be given by this Poisson bracket with the Hamiltonian. In particular, it means that if this Poisson bracket is 0, then and the function is not explicitly dependent on time, then this quantity f would be a conserved quantity. Okay, so it's 17 past, so let's resume. I want to focus a bit on what we said just before the break. So just to emphasize here that what we found out is that the time derivative of f, if f does not depend on time explicitly, then this term is 0. And furthermore, if f Poisson commutes with the Hamiltonian, then the entire right-hand side is 0, which means that f is a constant of motion. And this brings us back to Noether's theorem, where we discussed constant of motion and the relation to symmetries. I'm going to get back to that next time as well. But for the time being, I just want to give a few examples here of the use of this this equation for the time derivative of f. So in particular, if we look at the Hamiltonian itself, so what we have is that if the time derivative of the Hamiltonian is equal to 0, then so the explicit time derivative, so the Hamiltonian depends only on p and q and not explicitly on time, then the total time derivative of the Hamiltonian, well, that's going to be the Poisson commutator between h and itself. And since the Poisson commutator is antisymmetric, this has to be equal to 0. So this tells us that if the Hamiltonian does not depend explicitly on time, then it's going to be a constant of motion. And as we saw in the beginning of last hour, the partial derivative of the Hamiltonian with respect to time was directly relatable to the partial derivative of the Lagrangian with respect to time, which corresponded to the conservation of the total energy. So we have something similar going on here. The second example is angular momentum. So if we consider the motion of a particle in 3 dimensions, so motion in 3D, so our Hamiltonian in that case is going to be p squared divided by 2m plus the potential. So the total energy is essentially, right? And the angular momentum is defined as x cross product with p, or if you will, in terms of components, Li is going to be epsilon ijk xj pk. So this means that if I take the time derivative of L, because L is a function of x and p, this is going to be given by the Poisson commutator between L and H. So if I write this out, what we have is x cross p, and I have the Hamiltonian here, p squared divided by 2m plus v of x. Now, since p Poisson commutes with itself and x Poisson commutes with itself, essentially I'm going to have two terms left here, and if I compute them, I get 2p cross p over 2m minus x cross the gradient of the potential. So this computation is a little bit more detailed in the lecture notes, but this is what you get in the end. So in particular, p cross p is equal to 0, so this term vanishes. And if we look at what's left here, minus gradient of v, well, that's the force that's acting on the particle. So what we end up with is x cross f. And you might recognize this as the torque. In particular, if the potential is a central potential, so it depends only on the radius, then this force is going to be in the radial direction. That is, it's going to be in the same direction as x, and the torque is going to be 0, which means that angular momentum is going to be conserved. So that's about that. That's two examples of how you can use this. Any questions on that? Okay, so we discussed the relation between equations of motion now. Between constants of motion and how they these functions commute with the Hamiltonian. And there is actually a way that we can use the Poisson bracket to generate possibly new constants of motion. So generating additional constants of motion. So what we can do is the following. So we're going to assume now that f of q and p and g of q and p are constants of motion. So this is as we saw, this is equivalent with saying that f, the Poisson commutator with the Hamiltonian, is 0, and the same thing for g. So both f and g Poisson commute with the Hamiltonian. Now, if we look at the Poisson commutator of f and g, we're going to see that this is also then a constant of motion. And if it's independent of f and g, if we can't write it in terms of f and g, then it's a new constant of motion. So just to see that it is a constant of motion, let's take the time derivative here and figure out what it is. Well, the time derivative of anything here, that's going to be its commutator with the Hamiltonian. But now we can use this Jacobi identity that we discussed when we introduced the Poisson bracket. So if we just use the Jacobi identity, what we find out is that this is minus HFG minus GHF. So we now here have some commutators of F and G with the Hamiltonian, but we know that they were constants of motion, so those commutators were both equal to 0. So this is equal to 0, which shows that if both F and G are constants of motion, then their commutator is also a constant of motion. So just to take an example of that, I'm going to come back to the angular momentum, or rather its components. So angular momentum components. So in particular, if I take two of the angular momentum components, so let's take Li and take the commutator with Lj. So just writing out these components, I get epsilon I Lk, epsilon j, and let me use the same indices as I used in the notes because it's going to be much more legible. XLPK, XMPN. Here I've just introduced the expression of the angular momentum components in terms of X and P. So if I take this Poisson bracket and I do this computation, it's also detailed in the lecture notes. What I'm going to end up with is xi pj minus xj pi. And one can convince oneself that if we multiply L by epsilon by this permutation symbol, we're going to see that this is equal to epsilon ij k times Lk. So this tells us that the commutator of two of the angular momentum components is proportional to the other angular momentum component, which also tells us that if we have two of the angular momentum components conserved, then also the third component is going to be conserved. So we can't have just two of the angular momentum components conserved. If two are conserved, then all three are conserved. However, you can have just one conserved, and the two other being time dependent. Right. So, any questions on that? If not, let's go on. And what I'm going to do now is I'm going to introduce more general phase space coordinates. So what we've seen so far is that we can write down everything in phase space. We have so far labeled our coordinates Q and P, so the canonical momenta and the generalized coordinates. However, let's write that down, generalized or general phase space coordinates. So together we have these QIs and the PIs. I've always written Q and P. However, I could just introduce a new set of names for these coordinates. So we can introduce YA. I mean, that's just choosing a new name and for all of the phase space coordinates, such that yi that's equal to qi and yi plus n is equals to pi. And here, I mean, I goes from 1 through n, and a is then going to go from 1 to 2n. So this defines all of the y's, and it's just a collective name for p's and q's. Now, in general, since both qi and pi they satisfy this this general equation of motion, I'm going to have that y dot a is equal to ya Poisson commutator with this. I mean, this is true for any function of p's and q's, and in particular, these y's are functions of p's and q's. And I can then introduce the commutator between y's. So I can compute the commutator between ya and yb, and we're going to find out that this is delta a b minus n minus delta a minus n b, and this is something that I can define as omega ab. And you see that this is something that's anti-symmetric. In particular, if you write it down, it's going to have zeros on the block diagonals, and it's going to have something that's proportional to identity in the off diagonal and something that's proportional to minus identity in the other off diagonal. And we can also write the Poisson bracket between any two functions. I mean, f and g are now functions on phase space, so they are functions of the y's. We can write this Poisson bracket as omega ab df dya dg dyb. And I mean, you now see the kind of relationship that we have to what we discussed in the first two lectures, where we discussed general coordinate transformations and stuff like that. Here we have something with two indices downstairs. We have some generalized coordinates y. This omega here with the indices upstairs is going to turn out to be a rank 2 tensor. It's called a symplectic form in general. And in this Hamiltonian mechanics, it plays a similar role to the metric. I mean, it doesn't tell you about distances, but it tells you something about how this phase space works. Okay. So that's just discussing a bit this how you can introduce some general coordinates on this phase space, that we don't have to write always p and q. We can introduce some other coordinates which we call y. Questions so far? So let's just take a quick example of that, which is like if you have a particle in 1D. So a particle moving in one dimension, what we would put is that y1 would just be equal to the coordinate x, and y2 would be equal to its canonical momentum. And if you look at the Poisson commutator here, between two functions, it's going to be df dy1 dg dy2 minus dg dy1 df dy2. So this means that omega 1 2 is equal to 1, omega 2 1 is equal to -1, while omega 1, 1, and omega 2, 2 are both equal to 0. So you have this anti-symmetric omega. Okay, so the next topic is what is called canonical transformations. And if you remember your Euclidean geometry, you remember that we defined rotations as coordinate transformations that preserve the metric. In the same sense, we're going to define canonical transformations as any transformations that preserve this form of the Poisson commutator. That is to say that this omega is going to take the same form in all of those coordinate systems. So we can always make any arbitrary coordinate transformations in phase space, but these canonical transformations is going to be a particular form of coordinate transformations. So we will consider the following. Transformation. So we're going to take YA and we're going to map it to some new functions, capital Y, which depend on the Y's, or equivalently, we're going to let QI go to some capital QI that depends both on Q and P, at the same time as PI goes to some capital PI, which also depends on Q and P in general. And such a transformation is called canonical. If the Poisson bracket is conserved. So what does this mean? Well, it's going to mean that if we take the Poisson commutator between QI, capital QI and capital QJ, and the same thing with PIs, sorry, we should have indices upstairs here. So I and J. This is going to be the same as PI, PJ. Both should be equal to 0. And if you take the canonical commutator between capital QI and the capital PJ, it's going to be delta IJ. Or if you wanted to write it in terms of the Y's, should have that the YA and the YB commutator should be omega AB. Now, this corresponds, if we write it out, to writing that the commutator between YA and YB, if we just take the definition, is going to be the YA, the YC, the YB, the YD, omega CD, and this from this relation is equal to omega AB. And you see now, if you just look at this expression, it reminds us very much about the coordinate transformation properties of tensorial components. So essentially, this thing here is the transformation rule for omega, and saying that it's equal to omega AB just says that the components should be invariant under canonical transformations. So I mean, if you take any two functions, f and g, so this also means that if you take f and g as functions on phase space, and if you take the Poisson commutator as defined in terms of the previous variables, this has to be equal to the Poisson commutator if you express f and g in terms of the new variables. So let's look at an example of a canonical transformations. And this example is called phase space rotations. So for one-dimensional motion, we had this example before where we expressed this omega. So let's check if we can make a rotation in phase space that is going to be preserving this commutator. So I'm going to define here our new x variable. I'm going to define as x multiplied by some cosine of some angle alpha, some fixed angle alpha. And I'm going to add to this something that's proportional to the canonical momentum p. But since generally they will not have the same dimensions, I'm going to multiply by some arbitrary constant beta, which will take care of the dimensions for me. And then multiply by sine alpha. And at the same time, I'm going to define my new p as a similar thing. So x divided by beta. Again, this beta is going to take care of the dimensions for us, times sine alpha plus p cosine alpha. So this is essentially a rotation in phase space. If you remember from when we discussed the phase space for the harmonic oscillator, we had here the one-dimensional, the phase space for one-dimensional motion, and essentially what we are doing is that we're rotating the entire phase space. We're calling our new x variable something that is a combination of x and p, and our new p variable is also something that's a combination of x and p in such a way that we just rotated the phase space. So let's check if this transformation is canonical. I mean, it is a transformation, but let's check if it's canonical or not. So being canonical means that I should preserve the canonical commutation relations. Now, clearly, just because of the anti-symmetry, both the commutator of x with itself and the commutator of p with itself is going to be 0 by default. So those we don't really need to check any further. But what we do need to check is whether this Poisson commutator between x and p, well, if it's a canonical transformation, this should be equal to 1. So let's just check that. So we have x cosine alpha plus beta p sine alpha. And we take the Poisson commutator with x over beta sine alpha plus p cosine alpha. Now, if we look at the first term here in the first argument of the commutator, the only thing it has is an x. And we remember that this Poisson bracket is linear. And so I can just check them each term separately. So I have an x here. The Poisson commutator with this term is going to be 0 because x Poisson commutes with itself. However, the second term here has a p. So if I just move the constants out, I have a cosine in both of those expressions. So what I'm going to get is xp cosine squared of alpha. And if I look at the second term here, well, the commutator between this term and this term is proportional to the commutator of P with itself, which is 0. So what I'm going to be left with is minus, and the betas cancel. So I will have minus sine squared alpha, and then the commutator of P and X. So this, because of the canonical commutation relations for the lowercase x's and p's, is equal to 1, and this is equal to minus 1, which means that what we have is just cosine squared alpha plus sine squared alpha, which is indeed equal to 1, because of the trigonometric form. So this phase space rotation indeed is a canonical transformation. So any questions on that? I'm going to take one more example. We'll take up most of the rest of the lecture. Oops. Okay, so let's go to that example instead. So one thing, one special kind of transformation that we would like to look at is that when we look at the Lagrangian formalism, we know that we can make different kinds of coordinate transformations in the Lagrange formalism, and it works perfectly well. What we would like to see is whether the corresponding transformation in the Hamiltonian formalism is canonical, because if it's not, then the entire formalism would be on a bit of shaky ground, because you would end up with different equations of motion depending on which coordinates you choose to do this transformation. So let's actually look at the transformations in configuration space. Of configuration space with a corresponding transformations of the canonical momentum. So what I'm going to do is that I'm going to consider the case where I make a transformation in configuration space. So that is to say that I'm just making my new generalized coordinates depend on the old generalized coordinates. So they should not depend on the canonical momentum. So what I will consider is that I take my generalized coordinates and I transform to some new generalized coordinates which only depend on the generalized coordinates themselves. So no p dependence. Okay, so what does this tell us? Well, what we're going to find out, or what we need to find out, is what this means for the transformation that this occurs on phase space. So the first thing I'm going to do is I'm going to look at the time derivative here of the new coordinates. Now, I can just take the chain rule here and say that this is going to be equal to q dot j, and I'm going to have dqi dqj. I mean, this is just from applying the chain rule. This is taking the time derivative of capital QI essentially. So this means that if I look at the canonical momentum, or rather the capital canonical momentum, so I'm taking the canonical momentum now in the capital coordinate system. If I look at pi, I'm going to define this as the L dqi dot. Now, this is equal to the L, the Q dot J times the Q dot J, the Q dot I. However, the Lagrangian in general depends also on the coordinates themselves. So I'm going to have another term which is the L, the Qj, and then the Qj, the Q dot I. Okay. However, so in general, this guy is non-zero, but since this relation, this transformation between the capital Q's and the lowercase q's, it only depends on the Q themselves. So I can invert that transformation, which means that my lowercase q cannot depend on the derivatives of the capital Q's. So that means that this term is going to be equal to 0. So I'm only going to be left with the first term. And if I look at the first term, if I look at this thing, the lowercase dot divided by the capital case dot, I can look at Q dot as a function of the capital Q dots. And I'm going to have a similar relation as this one. So what I'm going to have is the same thing. If I take Q dot I, that's going to be capital Q dot J, the Q I, the Q J, for the same reasons. Q can be written as a function of the capital Q's. And if I take the derivative now of Q dot, lowercase q dot, with respect to Q dot, well, this thing, again, it only depends on the coordinates themselves, not the time derivatives. So I'm just going to get the time derivative here. And when I differentiate that, all I'm left with is this form. So what I am left with is essentially that this is sometimes called canceling the dots in this derivative. So this derivative becomes the same thing, just without dots. So what I end up with is the L, the Q dot J, and then the Qj, the Qi. However, the first term here we just recognize as the canonical momentum in the lowercase coordinates. So this is actually Pj, the Qj, the capital Qi. Okay, so that's our transformation. So I have now expressed my capital canonical momentum in terms of the lowercase canonical momentum. Now that we have done that, we can go and look at the canonical commutation relations. So if we look at, for example, the commutation between different Qi's, so the Poisson commutator between capital Qi and capital Qj, well, both of these capital Q's depend only on the lowercase q's. So when we take the Poisson commutator, we don't have p's anywhere, and since the Poisson commutator, each term contains derivatives with respect to p, this has to be 0. Okay. On the other hand, if I take the Poisson commutator between our new canonical momenta, I can just insert this expression here for that. So what we have is pk, the qk, the capital Qi, and then pl, the ql, the capital Qj. And again, we can use here the Leibniz rule for this Poisson bracket, and pk Poisson commutator with PL is 0, and in the same way this and this derivative, they're just functions of the q's, so their Poisson commutator is also going to be 0. So we can write this down as the qk, the qi, pl, and then the Poisson commutator between pk and the ql, the qj, and the second term, which is pk, the ql, the capital Qj, and then the Poisson commutator the qk, the qi with pl. And we just have 4 minutes left, so I'm not going to go through the entire computation, but if I just jump a few steps, what we're going to end up with, and again, the entire computation is in the lecture notes. What we end up with is the following. So pk multiplied by the second derivative with respect to the qi, the qj, minus pl, and essentially the same second derivative. And the only difference in those two terms is what we have called the summation index. So this is indeed equal to 0. So the Poisson commutators of the q's with themselves are 0. The Poisson commutators of the p's with themselves are 0. The remaining thing is the Poisson commutator between the q's and the p's. Now, if we compute this, what we're going to find is dqi, dqk, and then pk acting on pl, dql, dqj, right? Because the second term here will have a derivative of the capital Q's with respect to P, and they don't depend on the P's. And since this here does not depend on P, the only derivative that's left is the derivative of PL here. So we're going to end up with dqi, dqk, and then from this derivative we get delta LK. So we get the qk, the qj. Sorry about the misindexing here. That should be kept in this upstairs. And this again now is just a chain rule. We end up with the qi, the qj, which is delta ij. So indeed, this transformation from having a coordinate transformation in the generalized coordinates and using the corresponding transformation of the canonical momenta indeed gives us a canonical transformation. So indeed we have a canonical transformation here.